Optical Network Masterclass, prepared by engineer Adil Sally. Overview. This course is designed to build a precise, practical understanding of modern optical communication systems. We will examine exactly how data is converted into light, transmitted, and controlled across global infrastructure. Our roadmap follows the physical reality of the network. We begin at the microscopic level with the physical behavior of light waves and fiberglass. From there, we scale up through laser technology and pure optical amplifiers, concluding with the high-speed macro hardware that routes real-time data. This bottom-up approach is necessary. You cannot effectively design or troubleshoot a macro-level transport network without first understanding the absolute physical limits of the photons and optical paths it relies upon. The foundational constraint of any optical network is the medium itself, the physical fiber optic cable, and exactly how its internal geometry traps and guides light. Single-mode fiber uses a microscopic core, whereas multi-mode is wider. The outer cladding boundary forces light to reflect internally, creating propagation modes that trap the bits. The light's path is determined by the refractive index. Step index bounces sharply, graded index curves smoothly. For long-haul, high-bandwidth transmission, single-mode step index fiber is strictly required. Restricting light to a single direct path prevents signal dispersion. Dispersion is the blurring and overlapping of data bits over distance, destroying signal integrity. Before any routing software or transmission hardware is applied to a network, the physical glass geometry sets the hard limits on both data capacity and transmission distance. Running a single stream of data bits through a single physical fiber is vastly insufficient to handle modern global bandwidth demands. The solution to this capacity limit is wavelength division multiplexing. Multiplexing is the engineering process of combining multiple distinct signals into a single medium. In an optical network, this means transmitting multiple parallel data streams simultaneously through the exact same fiber, by assigning each stream a different color or frequency of light. This chart visualizes multiplexing. The top half illustrates CWDM. Notice the 20 nanometer gap separating each color peak. This spacing is inefficient and wastes spectrum. To maximize capacity, engineers developed DWDM. The bottom section shows DWDM nesting channels together, reducing spacing to an ultra-tight 0.8 nanometers. Isolating and processing distinct wavelengths separated by only 0.8 nanometers requires extreme precision. Optical networks rely on highly calibrated lasers to emit exceptionally stable frequencies, ensuring these tightly packed data streams never overlap or interfere. By manipulating the light spectrum with DWDM, static glass tubes were scaled into terabit capacity data highways, expanding the network's volume without laying new physical cables. As light travels over hundreds of kilometers, it inevitably loses power and fades. This natural energy loss is known as signal attenuation. The legacy solution to attenuation was the electronic repeater. This required capturing the fading light signal, converting it into electricity to boost its power, and then regenerating it back into a new light wave. This constant conversion created severe latency and physical hardware bottlenecks. Modern networks bypass this by using pure optical amplifiers. Here, the signal is boosted entirely within the photonic domain. The fading wave enters the amplification unit and immediately emerges as a high-amplitude wave, completely skipping the electrical conversion step. There are three primary categories of optical amplifiers used to achieve this: fiber optical amplifiers, or FOA, Raman amplifiers, and semiconductor optical amplifiers, or SOA. Selecting between FOA, Raman, and SOA depends entirely on strict system criteria. Engineers evaluate the specific physical distance the signal must travel and the precise power output required for that individual network link. Removing electronic conversion from the signal path and relying strictly on pure optical amplification is what makes high-speed, continent-spanning communication mathematically possible. We move now from the physics of the optical pipeline to the hardware nodes that orchestrate these multicolored streams at major network intersections. This schematic details an optical transport node. On the left, IP routers feed data into client interfaces. These are multiplexed into a consolidated line interface, feeding directly into the optical transport system. In the center sits the ROADM, the dynamic traffic controller of the optical core. The ROADM has the mechanical ability to extract, drop, or redirect highly specific colors of light onto entirely different physical fiber paths. Crucially, it routes these individual DWDM channels without interrupting the rest of the multicolored light stream passing through the node. By routing specific wavelengths on demand, ROADMs upgrade the physical layer from static point-to-point pipes into a highly programmable, dynamically routed grid. We can now zoom out to observe how the physical fibers, DWDM spectra, amplifiers, and ROADM units integrate to form the complete global transport topology. This topology maps end-to-end flow. Massive aggregation originates in data center networks. Tracing downwards, the signal enters the metro ring, where ROADMs manage core traffic. Finally, it arrives at the access network OLT, splitting into streams that terminate at individual ONUs for local edge delivery. This is the architecture of modern telecommunications. We scale global data by understanding the physical limits of light inside a fiber, packing it densely via DWDM, sustaining it with pure optical amplification, routing it dynamically through ROADMs, and delivering it hierarchically to the local edge.